All right. It's a little loud. I have a fan hidden under the desk just to cool me off. It's really warm this afternoon. This is my second time attempting to record this. Last time the trucks decided to run almost all evening. I think it's because Manoa Falls um, hiking trail is being redone. That's why the trucks are running like crazy. So I apologize. This needs to come out, so we're going to do the best we can. I will try to speak a lot louder. The mic is right here off. You see this? Right off the screen, right against my mouth. I mean, I feel like I'm about to swallow it. Um, so hopefully we can get this done. So attempt number 2 at chapter 4. And chapter 4 is a really cool chapter because for the first time since we began this class, we're going to be talking about things that have consequences. Uh, Part of the problem with chapter 1 and 2 was that that it felt like we're doing a lot of describing of statistics rather than actually bringing this information out into discernible chunks. We can actually do something with it. So that's the big thing. So in chapter 4, let's start looking at it. In chapter 4, before we get to the examples, and this was posted on Piazza once, on page 60, there's a definition of a probability distribution. And I cannot stress this enough. This is absolutely important. So let's try this. Absolutely important. When we are talking about a probability distribution, we have some value and some probability. And a dead marker. Some values and so value for an an outcome that we are looking for and the probability of that outcome. And we could have 1, 2, 3, 4, 5, 6 in case of a die, and then the probability of each side would be 1/6. Of course, as much as this is useful, it's not very fun. So if we look at a second one, let's look at something smaller. Let's look at a coin flip. So we have heads and tails. Let's call it 0 and 1 for the actual value. And then say we have, which means that the coin is weighted and tails are much more likely to happen than heads, right? So this is a probability distribution. How do we know that? Well, we know that the probability of any of the events is smaller equal to 1. And probability for any of those events is greater or equal to 0. As in, every event can either not happen, 0, or always happen, and that's 1, or something in between. And this is very, very important, the in-between part that this. One of the neater ways to write it is this. But it's a coin, right? It's a coin. We're going to flip it, which means that assuming we have no edge, and based on the values here, we cannot have an edge stand, so it's either one or the other side. This coin always lands on one or the other side, which means that the sum of all the probabilities needs to equal to 1. Well, what does this mean? It means that if we flip a coin, and we can pick any coin we like, there's plenty coins to choose from. If this coin has a probability distribution and the edge is not included, means it's always going to end up heads up or heads down or tails up. One or the other. Always. Which means that the moment you flip it, you end up in this table. And this little thing is very important. means that it always ends up one or the other in case of heads and tails, which also means that each one of those has a chance of happening. Now we could, in the same kind of conversation, have something like this. What does it mean? Well, it means that this, let's call it a coin, just like we did before. This coin always ends up heads. It has two sides, but tails never come up. Right? And again, can I have this at 1.1? No, because there's not 110% chance of something happening. There's 100%, 0%, or something in between, right? This is important, right? Okay, so the third case is looking at this, and we could have something like this. Is this a probability? Oh, we add all of them up, and this ends up to 1, which means it ends up on this coin. Tossed coin has some result in our table, but there's two problems. Problem number one is this, and we already talked about it, that there's no 110% probability that something happens. Somebody says 110% effort, bullshit. They just measured it wrong, right? So this is bad. Second bad thing about it is this. What does it mean it has negative 10% chance of happening? Negative 10% chance of something happening is what? Well, it's nonsense. It's not even, it's impossible. It's just nonsense. We cannot have negative probability. Either something happens, doesn't happen, or there's a chance of it happening. There is nothing that we can describe as negative 10% chance of happening. Right? So this is paramount. This is page 60. It's the bottom. It's section 4.2. It's the bottom of page 60. Like, if this is a problem, you need to talk to us on Piazza, because if you don't get this, nothing from chapter 4, 5, 6, and 7, and 8 will make sense. All right. Now that the spiel is done, let's see if we can find some examples to do. Scrolling. Example. Oh, there's example 1 on the next page. Hang on, let me just blow it up so I can see it. Zoom. Oh, perfect. Example 1. A fair coin is tossed twice. Let x be the number of heads that are observed. Construct a probability distribution for x. Alright, well, so probability distribution will look something like this. And x is the number of heads. We could have 0 heads, right? We could just get 2 tails. We could have 1 head. And we could have 2 heads. Cool. And now what? Well, now we need to find the probabilities for those. Now, how do we do it? Well, one way to do it is to consider, because it's a small experiment in a big ass truck. Sorry about that. All right, because it's a small experiment, we can look at it as the sample space for this is either tails, head, tails, tail, heads, or head. Right? And now we can take a look at how many ways can we roll out 0 heads out of this. Well, there's only one way, right? Out of how many? Out of 4. So 1/4. How many ways can we get 1 tail? We could get 1 tail here and 1 tail here, right? That's going to be 2 out of 4, and then 2 heads, 1 out of 4. Right? Again, because we said it's a fair coin, we implying 50-50 chance of heads versus tails, no edge, no funny business. And then find the probability for at least one head is observed. So now we are asking for probability that x is going to be greater equal to 1. Well, it's a small experiment, so that should be relatively easy to do. So what we can do is probability of at least 1 means probability of 1. Oh god. No, that's not a big truck, that's a small man. Probability of 2, right? At least 1 means this or this. Alright, well, that's 2 out of 4 plus 1 out of 4, that's 3/4. Easy enough. But last time I've been screaming at the mic saying at least 1, think about at least 1 as 1 minus probability of none. Probability of at least 1 equals 1. So let's do this. So probability of x greater equal to 1 equals to 1 minus probability of 0, which equals to 1 minus probability of 0, 1/4, which is 3/4. Ta-dam! So this was example 1. Alright, I hope there's no extensive questions here. Moving on. I'll put it. Where can I put it? Let's put it right here, just in case you're slowly copying things, or I need to refer back to it. All right, let's get another page. Example 2. A pair of fair dice is rolled. Let x denote the sum of the numbers of dots on the faces. Construct a probability distribution. Okay, so A is probability distribution, and x denotes the sum of the number of dots. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Again, I'm assuming they mean 6-sided dice, and now we need to do the probabilities. Okay, this is getting tricky. Now, I'll start with the obvious one. How many ways can this rolling 2 dice can happen, right? Well, if you think about it, we could have, let's put it over here. We could have 1, 2, 3, 4, 5, 6 on one die, and we could have 1, 2, 3, 4, 5, 6 on die number 2. And then if we took a look at it, this will be 2 dots, 3, 4, 5, 6, 7 dots, right? So what I'm writing in red is the sum of dots, where black one is die number 1, and in blue is die number 2. Alright, so we can fill this out. 1 plus 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 6, 7, 8, 9, 10. Yeah, it brings me to a joke. Why is 6 afraid of 7? 7, 8, 9. 2, 7, 8, 9, 10, 11, 8, 9, 10, 11, 12. Or if you prefer a different one, what did 0 say to an 8? Nice belt. Alright, so now we're done with this. There's 36 choices here, which means that each one of those probabilities will be some fraction out of 36. Well, how many 2s? There's only 1. So 1 out of 2. Same with 12. You can only get 12 if both of them rolls 6, so that's 1 out of 36. Well, let's see. 3, we have 2. That's 2 out of 36. 4, we have 3. That's 3 out of 36. 5s, we have 4. 4 out of 56. 6 is 1, 2, 3, 4, 5. 5 out of 36. 1, 2, 3, 4, 5, 6. We have 6 sevens out of 36. 1, 2, 3, 4, 5, and then we go down 5 out of 36. 4 out of 36. 3 out of 36. 2 out of 36, and finally that's another not big truck. Alright. And we have this, and there it is. There's our beautiful probability distribution. In the book, I wrote the probability distributions horizontally just to save space, but you can just as well write them vertically, and there's no issue with that. Alright, find P of 9. So we're looking for Px bigger than 9. Well, bigger than 9 is bigger or equal to 9 is here, so that's 4 plus 3 plus 2 plus 1 over 36. Right? If you want to visually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Because we're looking at, that's a bad color. Do we have, excuse me, I'm going to get more markers. Success. All right. So what we're looking for, 9 or higher, we're looking for this little section. All right. So that was easy. Now let's look at C. Find the probability that X is an even value. Alright, well, what's even? 2, 4, 6, 8, 10, and 12. Well, let's see. That's 1 plus 3 plus 5 plus 5 plus 3 plus 1 over 36. So this came out to be what? 10 over 36, and this came out to be 10, 13, 16, 17, 18. Nine. Easy. That's B, that's C, we're rocking. So once you have a probability distribution, you can do a lot of really cool things. And discrete probability is kind of cool that way, because we have accounted for all the possibilities. We have all the possible outcomes available to us. Thus, we can start making big statements about the probabilities for those sets. So that's that. All right. Next question. All right. Example 3. The mean of a discrete random variable x. All right. Well, so we have x, p of x, -2, 1 to 3.5, and the probabilities are 0.21, 0.34, 0.24, 0.21, and we're looking for the mean I'm using mu because, again, it's a discrete random variable, which means we have access to all the data. There's nothing hidden from us. So what we can do is we can talk about this as a population. So we have this, and that's equal to the sum of x of p of x. No, there's two ways we can solve this problem. One is we could do it negative 2 times 0.21 plus 1 times 0.34 and so on and so forth. The problem is I'm dyslexic. If I start writing things out this, I will make a mistake. So for me, I need to simplify. So the way I simplify things, I write a column saying x p of x. And what I'm going to do is I'm going to multiply these two together. And for me, that's a lot easier to be done than writing things out. Because if I write things out, I'll make a mistake. So you can do this way, and the example solution looks this. But what I do personally is I multiply those two. And that's negative 0.42. And that's 0.34, and that's 0.48, and that's where's my calculator? 3.5 times 0.21, and that's 0.735. And what I do is I just sum it up here, and that's equal to plus 48 plus 0.34 minus 0.42, 1135. It's the exact same procedure as this, just here you have to keep track, and you're doing plus 2 times 0.24 plus 3.5 times 0.21, and if you multiply this whole thing out, you are going to get 1.135. It's the exact same thing. For me, this is easier, just because I got extra cool features like dyslexia or stuff. Alright, so that's question 3. Question 4, or example 4. Example 4. A service organization in a large town organizes a raffle each month. 1,000 raffle tickets are sold for $1. Each has an equal chance of winning. First prize is $300, second prize is $200, third prize is $100. Let X denote the net gain from purchase of one ticket. Okay, so let's see, we have 1,000 tickets. We have $1 each. By the way, easy way to tell if the person talking to you is European or American. Europeans tend to write this, Americans tend to write the $sign before. Talking about priorities. Alright, each one has equal chance of winning. First prize gets $300, so first price is $300. Second prize is $200. Third prize is $100. All right. Well, so what do we get? Well, we get what are the chances of winning? if I say probability of one ticket, that's 1 out of 1,000 will get me $300 one. So let's say this is 1. Then 1 out of 1,000 gets me the price number 2, which is $200 one. And 1 out of 1,000 wins me $100. And then for 997 out of those 1,000, I'm going to be down $1. Or I'm going to win 0. I'm going to win 0. This is winning. And then the cost of each one of those, regardless if you win or not, the cost for each is that $1. Yeah. So what do we have? Well, if X is the node, so if X is net gain, then in our setup, here, right, we won 300, but we paid $1. In the second one, we won 200, and we paid $1 for it. And the third one is we paid $1 and we won 100. And in the last one, we won 0 and we paid $1. Right? The mentality problem in this kind of example, and again, I'm not looking at the solution, so I'm not sure what I put when I was putting the book together. What the problem becomes here is the mentality. And again, for me, it's easier to separate it, make some kind of a value X prime called, and just talking about the winnings, just talking about the positive gain. This way I can organize the table relatively quickly. But if I want to talk about net gain, right, which is how much did you win minus how much it costs to win, then I will start building this table out. And this is the net gain, right? So in our case, this table is going to look like this: 299, 199, 99, and then minus 1. Probabilities probably still stay the same because that hasn't changed. Picking that one magical ticket out of a whole set of 1,000 of them, right, still is the same. Now, what does this ticket represent is what we are talking about on top, right? I could be talking about how much did you lose per se, and again, you would have this kind of same construct, because in each one of those cases, your chances of losing are exactly the same, right? You lose that $1 because this is a kind of an entry point to be in this raffle. So again, this is 1 out of 1,000, 1 out of 1,000, and this comes out to be 99 out of 1,000. No, sorry, out of 1,000, out of 1,000, out of 1,000. Right, and again, same thing here. 1 out of 1,000, 1 out of 1,000. Right. So again, you start building your structures any way you want. But at the end of the day, if it tells you X has to be net gain, X has to be net gain, and you're building things accordingly to this. All right, part B. Find the probability of winning any money in the purchase of one ticket. Well, any money is this, because the raffle doesn't specify, you know, pocket change. It specifies $100, $200, and $300. Well, so what's the probability? Well, 3 out of 1,000. Right? Because this is probability this, probability this, probability this. Or if you want to talk about chapter 3, this is probability of first, probability of second, probability of third. One or this, right? This is or. This is additional. And the last question is, find the expected value of x and interpret its meaning. The interpret part is going to be fun. So part C is, this is part B. Part C is find the mean. Expected value. Expected value also means the mean or the average. If, for example, on average you get, as a waiter, you get $20 an hour, what do you expect in hour number 2 to get? Not $20 an hour, right? So expected value, average, and mean, they're mean slightly different things, but the mathematical conclusions for that are very similar. All right, so expected value. Well, expected value, mean, is sum of x, p of x. Well, in our case, it's going to be 299 times 1 divided by 1,000 plus 199 times 1 divided by 1,000 plus 99 times 1 divided by 1,000 minus 1 times 997 divided by 1,000. So I'm just going to sum up the top. So this is 299 plus 199 plus 99. Can you see this? Okay. Minus 997. Bam. So this comes out to be negative 400 over 1,000, which is negative 0.4. And what does negative 0.4 mean? Well, it's not a probability. We are no longer talking about probabilities because we are talking about x times p of x. So what we are talking about here is we are talking about the expected value according to this probability distribution. And what does this mean? Well, what were the units here? Those were all in dollars, right? So this is in dollar. How much is that? 40 cents. And what does this mean? They tell you, give me negative 40 cents, right? Or you're going to get negative 40 cents. What does this minus mean? It means reverse, which means losing 40 cents. So if you see this distribution and you decide that you're going to be smart and you're going to buy every single ticket just so you have guarantee of winning, on average you're going to lose 40 cents per ticket. Right? This is what this means. This minus means that playing in this setup means you're going to lose. AKA house always wins in this. Yeah, the house is going to have to pay $300, $200, and $100 out. But when the raffle is done, they're going to rack up $400 a head. It's a really cool concept for people that gamble or think about gambling or think that gambling is a way to make quick money. Just make the calculation. There's a reason on the blackjack table it says that the dealer won't go above, I think, 16 or something. There's a reason why certain people, in poker, toss in good hands that you would presume to be good hands in the muck and not play it further. There's a reason why certain lotteries get bought out very quickly and certain lotteries aren't. There's a reason why certain stocks get bought out. I apologize. There's another person that has identity issues. Right? There's this concept that you can actually figure out if it's worth doing something. Right? And you can do it for raffles, but you can do it for a lot of other things. And what gets advertised a lot of the times is this. Oh my God, you're gonna make $300, $200, or $100 if you buy a ticket. Buy more. Yeah, the more you buy, the more you lose. Yeah, there is going to be a person who randomly picked up one of the tickets and won. Congratulations. But everybody else is losing, right? And again, this concept of probability is not taught to most people, which means that this math escapes, right? Again, we could construct this is a side note, we could construct this in such a way that the net is positive, which means gambling on this, I object to gambling on principle, but gambling to something that has a net positive makes mathematically a little bit more sense. So, for example, let's expand this and let's talk about same kind of setup. X, P of X, and let's say that instead of $300, you win 1,000. So this is 1. There's 1,000. There is 750. There's 500. And entry is $1, so you win 0. And again, 1 out of 1,000, 1 out of 1,000, 1 out of 1,000, and 997 out of 1,000. So we imagine we have lottery like this. Now, again, we want to go net gain. Net gain, we will have X, P of X, right? So far so good. And I'm going to change the marker and let's just calculate the expected value. Again, X, sum of X, P of X. And what do we have? Well, we have 999 times 0.001 plus 749 times 0.001 plus 499 times 0.001 minus 1 times 0.997. Alright, let's see what we get here. So 999 times 0.001 plus 749 times 001 plus 499 times 0.001 minus 0.997. Boom. Right? And what does this mean? Well, it means that on average, you're expecting to win $1.25 on every ticket. Win ahead, right? Because it's net gain. So you put in $1, you're expected to get $2.25 out. Now, does this mean that if you buy a ticket you're going to be $1.25 richer? No. That means that if you bought every single ticket for that lottery, every single one, you would make a killing on it. Because you would put in $1,000 to buy all 1,000 tickets, and you would come out with $2,000, $2.25, right? Again, that's the difference. And all it took, is increase the winnings. So when you see huge billboards saying, "Hey, play our lottery," on the mainland, they are very popular. You can win 128, 7, 8. And 82 cents. This looks impressive for the first prize. My question is, what's the number of tickets sold? If there's one ticket, that ticket is going to win this. Right? But if there's a lot of tickets, we're talking millions or billions of tickets, that price looks good. It doesn't look great, right? And again, stacking your odds of winning. Now again, in this case, only 3 tickets win, so you still have to consider the fact that 3 out of 1,000 is where you're going to make the money. But mathematically, this, if you're planning on gambling, this would make more sense than this. I'm not saying you should gamble. I'm against gambling. This could be a big problem and a big addiction, but right, if you're doing paper things with your friends for whatever, or raffles at your church or something, math, brilliant, ruins gambling establishments. All right, so that was example 4. Let's do 5 before this video balloons to, oh god, we are 40 minutes in and we're only on example 5. I'm slacking. Well, considering that this is me saying the same thing for the second time already, I envy my patience. All right. Example 5. A life insurance company will sell $200,000 1-year term insurance. Policy to an individual in a particular risk group for a premium of $195 premium. Find the expected value to the company of a single policy if the person in this risk group has 99, so the probability of something is 9997%. Oh, survival. Right. This 1-year term life. Okay, so $200,000 for a year at a premium of $195, and the survival rate is 997. find the expected value of the company. Value to the company. Value to the company, so I'm assuming they're talking about net gain. Alright, so what are the considerations? Well, there's two. 99.97% of the time, right? The person survives, which means that they cannot collect, so the company gains 195, right? This is right. If it survives a year, life insurance doesn't kick in, so we make money. Now the 300th of a percent, 300th of a percent of the time, the company has to pay out, right? Now they're losing it. That's the important part. They're losing it. But that person also paid the premium, right? So this is paid out, and this is the paid premium. So what is our expected net gain? This is getting excited here. Yeah. Fuck it. Okay. So what is our expected gain? Well, our expected gain is this. Well, let's see what comes out. Mu equals 195 times 0.9997 minus 200,000 minus 1 plus minus. Guys, I'm being stupid. Let's do this again. Focus, Jan, focus. It's embarrassing. Alright. It's sum of x p of x, which means that the mean equals to 195 times 0.9997 plus negative 200,000 plus 195 times 0.0003. So this equals to mu equals 195 times 0.9997, which is 194.9415 plus negative 12123 plus 195. That's negative 199,805 times 0.0003. So this equals to 194.9415 plus minus, so that's minus our number times 0.0003. So this comes out to be 194 minus 59. Which means what? Which means that this is the expected value the company is going to gain. This is the expected net gain per policy. Yeah, sometimes you need to bail out $200,000 out. But overall, you're making $135 per policy. So if you sell 1 million policies, you're ahead 135 million, assuming that this survival rate is maintained. Of course, if the survival rate crashes, the proportion here changes. But assuming that this works for the whole population, this insurance company is making a bank. On a side note, all the big companies that have those huge disasters happening everywhere are including this kind of conversion and conversation in their billing. It's price of doing business as it is. So for example, if I don't know, oil pipeline company, is building a pipeline, they're making this calculation saying, hey, sometimes the pipeline is going to break. There's a small chance the pipeline is going to break, and we're going to get sued from here to the moon and back. We do the calculation and be like, look at that, we're ahead. So we're just going to put some of the money aside for all the lawsuits, and we're still going to build the pipeline. Because, eventually we're going to make it out, right? One of the examples was Ford Pinto, I think was the car. There was a car Ford was making that they wanted to make 1,000 cars for $1,000, and they came up with $997 or $98 per car, and they were very happy about it. The problem is the car's back bumper and the gas tank were too close to each other, and so if there was a collision, the back bumper would hit the gas tank would explode, and people would burn alive. And so what the car company did is they made a calculation not unsimilar to this and said, hey, if we consider that we're going to get sued for people that got burned alive, for people that got super crispy, for people that got just injured, and for people that got really scared, and we reimburse them on this is how much it's going to cost us to do it. But if we have to do a recall or put in a replacement bumper, which was a rubber stopper costing I think $6 per car, and they made a calculation how many cars they are on the road, how likely are they to explode, and they said, screw it, let people burn, it's cheaper. And again, this is the same calculation. Philip Morris did the same thing in Czechoslovakia, or Czech Republic now. They went there and they were like, hey, your government is trying to raise the taxes on cigarette. And they did the following. If the taxes go up on cigarettes, people buy less. Which is good, right? Taxes are increased, the government is happy getting more money from it, people buy less, they're healthier. What Philip Morris said is, hey, if people buy less, people live longer. If they live longer, Social Security, or the equivalent thereof, needs to be paid out for more. It's like, Philip Morris says, hey, you increase taxes, you're going to get some money now, but you're going to have to pay out retirement for a lot longer, and you're going to lose money. It's better for you if you keep the taxes low, so people buy more cigarettes, so they live shorter, so they die earlier, so you can pay less retirement. Guys, this kind of conversation happens a lot, and it's just part of doing, business. This question is, what do you value? And if you don't value human life, this kind of calculation is very simple to make. Most insurance companies won't pay life support costs if they exceed, I think, 60 grand a year. So if life-saving medication costs more than $60,000 a year, so if you pay $60,000 in payments, if the insurance company pays you $60,000 to extend your life by a year and not more, they might not do it because it's just not cutting their bottom line. So if you take the human value of human life out of the equation and you just look at numbers, this is how it's done. Alright, I'm done soapboxing. If you want to know more, let me know. If you're curious about the links, I'll find some for you just to ruin your day. So, alright, oh look at that, we got the same number. Alright, definition. Now, the definition on page 64 for the standard deviation and the variance, those look scary, but just like before, they are very easy to do if you just split it up into pieces and just go for it. That's first. Second of all, you can get the calculation done for you. Again, there's calculators online that do this calculation for you, so you don't need to actually fight with all those formulas. If you see scary formulas and you can find a calculation online or a calculator online that does it for you, just plug in one of the examples, see if you get the same number, plug in another one, and then go and check with other things. I don't object to you using resources, just like that is a resource. What I object to is just mindlessly googling and plugging things numbers in and then expecting that just because you get an answer, that answer is correct. If you understand why the answer is correct or not, great, go for it. If you don't, you put me in a very awkward position. Don't put me in awkward positions. Example 6. Alright. 6. The discrete random variable x has the following probability distribution. -1, 0, 1, 4, 0.2, 0.5, a 0.1. Okay, a histogram that graphically illustrates probability compute the following qualities. Okay, that should be easy. What's A? Well, let's see. The sum of all the probabilities needs to go to 1. 0.5, 0.7, 0.8, which means A has to be 0.2. Right? Again, by definition, we talked about it, page 60. So that's A. B, probability of 0. Well, probability of 0 is right here, 0.5. C, probability of x being greater than 0. Well, greater than 0 is those two numbers, right? 1 and 4 are greater than 0. So, how much is that? That's 0.2. Write it right here. That's 0.2. Right? And then 0.1. So that's 0.3. Right? This plus this. This is our grade. The probability that x is greater equal to 0. Well, now we have to increase 0, so we expand this. So we're looking at this. 0.5, 0.7, 0.8. E, probability of x being smaller equal to -2. Well, we have -1 here, right? And so what's the problem with that? Where's this? This is somewhere here. Is there a chance, according to this table, is there a chance to get a -2 or smaller? No. 0. Next one. F. Mean mu of x. Well, again, mu equals sum of x p of x. So mu equals -1.2 plus 0 times 0.5 plus 1 times 0.2 plus 4 times 0.1. So that's -0.2 plus 0 plus 0.2 plus 0.4 0.4. Okay, F is done. G. What's G? Variance and then standard deviation. Alright, so G and H. So this is variance and this is standard deviation. Alright, let's take a new piece and let's get the numbers down here. Alright, we know that the formula for variance equals to sum of x minus mu squared p of x. Or if you look at this is page 64. Or if you look at the second one, it's equal to sum of x squared p of x minus mu squared. Now you have two choices. Both of them work. I like the second one better than the first one, and I'll show you why. Let's rebuild our table. .2 because we sorry, another big truck. 0.2 which we solved here, and then 0.1. Look what we need inside. We need an x squared and a p of x. So let's make a column called x squared. Well, x squared means squaring whatever is here and putting here. -1 squared, 1, 0 squared, 0, 1 squared, 1, 4 squared, 16. What's next? Well, x squared and p of x. So x squared times p of x. Well, what's this? 1 times 0.2, 0.2. 0 times whatever, 0. 1 times 0.2, 0.2. 16 times 0.1, 1.6. So if we go sum of x squared p of x, what do we get? 0.2, 0.4, 2. Right? So now we go this. And how much is mu? Well, we calculated mu here. So this equals to 0.02. And what's mu? Well, if mu equals to 0.4, mu squared equals to 0.16. 0.4 squared. So how much is this? This is and And there you have it. There's your variance. And again, either formula works. You can do it expanded. I like the table because for me tables are simpler to do because I have to do one thing at a time. And again, just like a Shrek, you open it up from the middle, you have x, you have p of x, and you just build, and you get this. Now for standard deviation, we could do the formula thing again, or we could just say, hey, this is h. This is just a square root of this, which means that this is a square root of 1.84, which means that this equals to clear 1. Square root of 1.84 1.356. And that solves it. Pretty cool. Well, if you want to go 1.565, if you want extra decimal place. Close enough. How cool was that? I think it was pretty cool. 6th example done. Section 4.2 done. We're moving on. Here's the whole thing. If you want to pause so you can actually work on it. Alright, pausing, done. Alright. Binomial distributions. Binomial distribution is so cool. The problem with binomial distribution with binomial distribution is people don't appreciate how powerful binomial distributions are. A lot of the universities that I know of don't teach it anymore. My mom, who teaches mathematics in New York, says binomial distributions get cut out from their syllabus because there is no good reason why, but they are. And binomial distributions are really, really cool. The following needs to be understood, that binomial distributions have a set number of procedures or trials that are being run. So you run a specific set of trials and that number doesn't change. The moment you go like, hey, how about we run a couple more, you have to throw out all your calculations out the window and do it from scratch. So that's one. Second one is, in binomial distributions, you only have two outcomes, and that's success and failure. And I'm not saying that one of the outcomes is a success and the other one is a failure. For example, if we talk about genders, like girls are success, boys are a failure, those are not implications about the actual outcomes. This is just the language we use. So you have two outcomes, success and failure, and we're going to be using those. And then the probability of success in each trial is independent from the previous ones, just like a coin. If you flip a coin, right, each time I flip, I have the same probability of getting the heads on this coin. This doesn't change. It doesn't have to be 50-50, but it doesn't change per flip, right? And it stays constant for the whole set of trials. So one flip doesn't influence the other, and they don't change on their own. So that's what's important about binomial probabilities. So you need to have that, and that needs to be coded in the back of your head. And there's a couple notation things. There's the n, there's the p, there's the q, there's the x, and then there's the p of x. And each one of them means a different thing. N means the number of trials, or the sample size, if you like. P is the probability of success in a single trial. Q is probability of failure, in a single trial. X is the number of successes, and P of X is the probability to get X successes. So this is number of trials. This is probability of success in a single trial. This is probability of failure. In a single trial. This is number of successes. And this is probability to get X successes. So this is the setup. All right. So this is one thing that we're gonna find in this section also is that, and this shows up in I think chapter 5 a lot more, is that we need to figure out if our sample or a number of trials is big enough for it to make sense. Like there's absolutely no sense if we are flipping a coin which has 99.999 chance of getting a heads and only a small fraction of a percentage chance to get tails. Flipping this coin one time doesn't make sense because you won't get the distribution clearly enough. So that's gonna come up soon enough. All right, let's look at page 68. And on page 68 you have this. And oh my God, I'm quitting math. Done. I spent 3 weeks being in this class and I worked so hard and there's not enough coffee ever to deal with this. Like, oh my. This is scary. This is relatively simple to deal with. And we're going to deal with it in pieces. And so part 1 is this, and part 2 is this. We haven't talked about this a lot in previous chapters, but what this is telling us how many combinations we can have of certain things. Let me see if I can. I'm assuming you guys remember those things. Now, this is cool, but we're gonna take this away because this is too big. It's too hard to handle. But let's look at this. There's a specific set of these things that we can come up with, right? And this is describing exactly that. So let me digress. Let me explain how did we come up with this, and then the rest of it will follow. So before we get to the first example in 4.3, let me do a little side spiel. And the side spiels looks the following. I'm going to put this over here, so it's still kind of hanging around, but we don't worry about it. All right. So the side spiel looks the following. Imagine you had a set of Scrabbles or a set of coins. Let's make sure that they're all different. And it's the same. Imagine we have a set of coins. They look different. These two look too close together. How about this? No, too shiny. All right, imagine we have a set of 4 coins. If I asked you to arrange them in a line, well, you could do it very easily, right? And each one of you would take the 4 coins and arrange it in some way. Now, imagine that I ask you how many ways can you arrange those coins in a line. Well, how would you do it? Well, you would go, that's one arrangement, right? And that's an arrangement. It's different than this one, right? So that's one arrangement. And then that's the arrangement. And that's the one arrangement, right? And then we could switch those, and then those, and I could probably switch those, and switch those, and switch those, and maybe switch those. Did we have this one? Right? And we start building this out. Well, that's one way to do it, and this is how we done it, building this. But how about we just think about it the following way? I have 4 places I can put those 4 coins on. How many choices do I have for the first place? Well, 1, 2, 3, 4. I have 4 choices for the place. Say I pick one. Done. How many choices do I have for the second place? I don't have 4 choices because I already picked one. So I have 3. How many choices for the second one? 2. And how many choices do I have for the last one? 1. And by the way, 1 is not a choice. 1 is you're stuck with it, like it's being the last kid at dodgeball. You're stuck as the last kid, right? So how many ways can I pick this? Well, I could have picked 1, 2, 3, 4, right? And so if something can happen number of times and then and again and then and again, what we get here is we get the number of arrangements this can make. And that's 4 times 3 times 2 times 1. 4 times 3, 12 times 2, 24 times 1. 24. So there's 24 arrangements of those 4 coins I could make. Alright, that was relatively simple. So how about we consider this from a perspective of somebody who has a lot of coins. If I tell you that each one of them is unique in one way or the other, and we could very easily make them unique, right? Heads and tail. So if I build here, how many ways can I arrange this? They're all unique. Well, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 unique coins. So 1, 2, 3, 4, and so on and so forth. How many choices for the first one? 14, 13, 12, 11, 10, and finally we have 2 times 1. Doing it for 4 is alright. Doing it for a lot more gets really annoying. Like, really annoying. So what do we do? So, as scientists and most great thinkers are lazy people, we say, hey, this keeps on repeating. How about we call it 4 exclamation point? 14 factorial. And what 14 factorial means, an example of it is on page 68, right? Means 14 times 13 times 12 times 11 times 10 times 9 and so on and so forth. And instead of typing 14 times 12 times 11, we can do 14, and on this calculator there's a PRB here, probability button. You can scroll over to the exclamation point, and boom, and you get a number. And by the way, that is a big number. If you have one of them bigger calculators, it's under math. Oh, that battery. Let's see if we can find the other one. Yeah, under math, you scroll over to probability, and there it is, under 4, right? So math, scroll over 4, there's a probability thing. If you have one of these, again, math, and you can find it under probability. Where's it? No, sorry. For this one, it's right here. There's a little focus. No, apparently it doesn't want to focus. Stupid. Anyways, there's a button with an exclamation point. If you have one of those Casios, I don't know if this one has it. Should have it somewhere. This one has different buttons we're going to talking about in a second, but I don't see the exclamation point. I'll look for it eventually. But they have it. Worst comes to worst, you just type it out. But that button exists because we tend to use it a little bit in most of the aspects. So that's one. Part of the definition we needs to consider is this. What does this mean? Well, this means how do you arrange 0 objects in 0 spaces? So let's say you moved out of your parents' house, right, to go to college or get married or whatever, and then you get an email from your mom saying go clean up your room in their house, that room that she converted into a studio or an art project or something. How many ways can you arrange or clean up a room that you don't have? Well, one way. You can't, right? How many ways can you arrange 0 pens on a table? One way, you don't arrange them, right? How many ways can you eat zero donuts? One way, you don't eat them, right? So this is by definition important. All right, so that's the factorial part. Now, there is a couple things to consider. One is if we... Too many coins. One thing is if we consider that out of our 4 coins, I want to arrange just 3 out of 4. I want to pick 3 and arrange 3 out of 4. So 1, 2, 3. How many choices do I have for the first one? I still have 4 choices. Second one, 3, and then 2. Right? Then again, if you multiply this out, that's 24. What happens if I want to arrange just 2 coins? Pick 2 at random and arrange them. Well, I could pick this one, and there's a bunch of arrangements I could do, or I could pick these 2, or these 2, or these 2, so I still have 4 choices for the first coin, 3 choices for the second, but I don't have the remainder of that tail, and I only have 12 arrangements. There's 12 arrangements of 2 coins out of 4, because I could go these, 1, 2, 3, 4, 5, 6, right? 7, 8, 9, 10, 11, 12. And there's your 12 arrangements. You cannot do anything more because every other one is something we already had before. So you have 12. And this kind of concept of losing that tail is prescribed in a formula that looks like this. And what this formula says is that the permutation of R objects out of N objects, there's this many. N factorial tells you how many arrangements could you make total. So in our case, 4 coins, that's 4 factorial on top. And on the bottom we say, hey, I want to only arrange 2 of them, right? So if we look at 4p2, I want to arrange only 2 of them. That's 4 minus 2. Let's call this x, so it's consistent. If I want to arrange only 2 of them, that's this. If I sort this out, that's 4 times 3 times 3 times 2 times 1 divided by 4 minus 2. 2 factorial is 2 times 1. And I cut off this tail right here. And you have that button on the calculators. It's called, on the calculators it's usually called NPR or NPX. One or the other. And it says, hey, I want to arrange X objects out of N objects. So that's this. Now, so that's part 2. Part 3, and again, this is, I'm blasting through it, so if you want to more, we can talk about it on Piazza, or you can look at some of my old lectures about it. The third choice is the following. Imagine I want to arrange 3 coins. How many ways can I arrange 3 coins in 3 places? Well, 3 coins in 3 places, right? 3 coins in 3 places is 3 factorial. What happens if those 3 coins turn into 3 coins? Here I could, this is a different arrangement than this. Yes, this is different than this. How about here? Can you tell the difference? If I went, did I change anything? Right? So what happens is if the coins are indistinguishable, or I don't care what their positions are as a whole, I lose this level of resolution I have here. So what happens here is I just say, hey, imagine I had 4 coins. So out of 4 coins, I want to arrange 3. And I don't care about what? Well, about order. I don't care how they are, I just care that we take out 3 of them. Well, how many ways can I do? So again, there's the 2 sets, right? I could take those 3, or I could take those 3, or I could take these 3, right? And so on and so forth. Doing it with this, it runs into a problem where you have to find which 3 you want, and then you have to ignore the fact that they have their own combination, because I could have picked up 1, 2, 3, or I could have very easily picked up 1, 2, and 3, and those 2 sets are exactly the same. If I don't care about the order, I don't care about which coins I'm picking up, I might as well look at a set that looks like this. Right? And if I look at a set like this, well, it matters if I pick up these 3. Sorry. I could pick up this 3, or I could pick up this 3, or this 3, but hang on, this and this is exactly the same, because I cannot tell the difference apart from the coins. And what we get is NCX or NCR, depending on which book and information you use, which says, hey, the following. Right? This is the NPR we talked about. And then we lose this resolution. And which resolution is this? Well, of the coins that we picked. And that's this. Because if we took a look at this set, right, and I chose 2 coins, so 4P2, we established that that will be 12, right? Picking 2 out of 4 coins, I showed you that you can get 12 sets. But now, what happens if I don't care if they're like this or like this? If I don't care this versus this, or this versus that, or these, right? I don't care how they arrange, I just care about 2 coins. Not this is the first coin, this is the second coin, I just care about 2 coins. Then out of this, I have to lose that resolution, and that's this right here, that 2 factorial. And that comes out to be 6. Alright, let's do an example for that, and then we're gonna move on. This is starting to balloon. Alright. Alright, we have 3 coins. Let's arrange those. Silver, bronze, gold. Visible? Visible. Alright. So we could arrange them silver, bronze, gold. We could arrange them bronze, silver, gold. I could arrange them bronze, gold, silver. I could arrange them gold, bronze, silver. Right? What else can I do? I could arrange them gold, silver, bronze. And maybe silver, gold, bronze. And that's it. That's my 6, right? I had 3 coins. I'm arranging in the 3 places. 3 factorial, 6. If you're watching my old lectures, this is the whole Billy, Bob, and James conversation. So let's say in this case, I have this. And I'm gonna how do I do this? No, let's do this. All right. I have this same coin. What are my options? Well, I could go silver. Let's call it double color, so double, double. I could switch them around, right? And I could get double silver, double, and I could switch those around and get double, double silver. I could switch these 2 around. Oh no, hang on, silver, double, double already have. How about we switch these 2? No, that's silver, double, double. How about, no, I already have that, I have this. So overall, I have only 3 combinations here. Why? Because these 2 coins are the same. So what's the difference between this and this? Well, this is 3P3, right? We're arranging 3 out of 3 objects. If you want to take a look at 3, probability P3, 6. Right? Where here, I'm trying to do 3P3, but 2 of those objects are exactly the same, which means I'm losing 2 factorial resolution. So if I divide this by 2 factorial, right? What is this 2 factorial? Well, that's the resolution I lose from these 2 coins. I get 3. Right? So what we're looking here is we're looking at a combination of x objects out of n. Now, why do we care? So I've been talking for 20, well, maybe half an hour about this, and it's like, why the hell do I even bother? Well, the reason why we bother about this is because what happens if you want to flip heads and tails, for example? Or right? Or pick stones. Now again, with the stones you have to be careful, because one of the rules for binomial probability distribution is that the probabilities cannot change, which means that you will have to infinite supplies of both stones in some proportion, right? So stones, problematic. Coins, on the other hand, not. So let's find a coin. Okay, can you tell the difference between heads and tails? Yeah, not very. Let's do this. How do we do? Cool, you can tell a difference. So we have a coaster, heads, tails. So the brown and then tan. So we have heads and tails. So let's say we want to flip the coaster 10 times, right? And we are wondering what's the probability we're going to get. We're going to get 4 10 sides. Well, so let's see. We could throw this around and we could have brown, 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 tan, brown, brown, tan, tan, brown, brown. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We could have this. This doesn't satisfy it, but on the next one we could have right that. Or we could have right, and suddenly these two satisfy it, these don't. So let's not worry about this one, right? But this arrangement, right, looks like an arrangement of 10 objects in 10 spaces, right, where we don't care about the arrangement, because you cannot tell the difference between flipping brown here and flipping brown here. It's still brown, right, versus tan color. So what we lose here is we lose some resolution here. And so if we considered flipping heads a success, what I'm really interested in is flipping 4 successes, right? So I'm looking at P of 4. So what I'm looking for is, out of 10 throws arounds, I'm looking for 4 successes. This is 10 minus 4. I'm looking at this formula right here, right? I'm looking at this. What is this? Well, this is 10C4. Combination of 4 successes out of 10 trials. And once you have this, well, now we're going to go probability. What's the probability of getting the success? Well, assuming this coaster is balanced, right? It has some probability. Let's assume P is 50%. So that means we have to succeed 4 times. Well, P to the fourth power. Why? Because it's success once, and then probability success another, and another, and another. And then we have to fail 4 times. Well, what does mean fail 4 times? Well, you threw this coaster up in the air 10 times. If only 4 times end up on one side, all the other times it has to end up on the back side. Otherwise it doesn't make sense. Right? If you flip a coin 10 times and you get only 4 heads, what happens the other 6 times? Well, the other 6 times you get tails. Right? So this is the n minus x, that's the 6. Right? This is successes. This is the failures. And this is the 4 successes out of 10 trials. Or the combination of. Right? Now again, for people that don't care, you see a formula, you're happy using it, go for it. For people that want to understand, this is kind of the process of considering it. So this formula really tells me, hey, there's a combination of x successes out of n trials, and then there's a probability of success times the, to the power of successes, the number of successes, times probability of failure to the power of the number of failures. That's all there is. This big scary formula really means exactly that. It means we tossing coins, flipping coins, or any other choice which has 2 sides. All right. So that's the big spiel about this. So let's look at questions, example 7. 17% of victims of financial fraud know the perpetrator of fraud personally. All right, so there's some 17%. This is example 7. All right, use the formula to construct the probability distribution for the number X of people in random sample of 5 victims of financial fraud who knew perpetrator personally. All right, so we're building our this. And what are the choices? Well, you could know 0, 1, 2, 3, 4, or 5. All right. Well, let's do this. We can use this formula, and it's great. Or we can find the button on our calculator. Now again, I promise you won't have to use this formula as much as you think you're going to have to use it, so just bear with me. If we use the formula, we're going to, for the, say, which one should we do? Number 3? Let's do number 3. So if you use the formula for the third one, it's going to be n is what? Well, our n is equal to 5 because we have 5 choices. Probability of success. We're going to define success as knowing your perpetrator. So we're going to say this. What's probability of failure? Well, if you succeed at 17% of the times, you fail 83% of the time, right? Chum chum chum. Our x, well, for us, the x is equal to 3. Let's try this. So if you use the formula, this is 5 factorial divided by 3 factorial, 5 minus 3 factorial times 0.17 to the power of 3 times 0.83 to the power of 2. Number of successes, number of failures. If we use the formula with using this is 5c3 0.1 to the third power 0.83 to the second power. And again, you're more than welcome to try it. If you don't have the exclamation point, then your math is just going to get a little bigger because it's going to be 5 times 4 times a big truck times 3 times 2 times 1 divided by 3 times 2 times 1 times 5 minus 3, that's 2, 2 times 1, and so on and so forth. But either way, either one of those works, and if you solve this, and I'm going to take a peek what did they get for the third one, is they got 0.0338. So that's what the book says. Let's see if we can come up with the same answer. Can you see the calculator? Good. This is 5 NC3 times 0.7 to the power of 3 times 0.83 squared. Boom. Boom. I got it. Close enough at least. All right, so this is really cool. How many of you feel like doing this for every single one? Hands up. Anybody? Everybody? All right. If you look at Laulima or Piazza for that matter, let's pull up Piazza, see what we have there. Excuse me. Alright, if you pull up Piazza and under General Resources, you scroll down to Table Packet, you're gonna get this big collection of tables. And what you want to do is you want to look at towards the end, there's a binomial distribution table. Let's see if this works. So that's the question. No, let's see. Hang on, guys. Ah, here it is. All right, so you see the table, and if we scroll down all the way down to the bottom, we get binomial get the binomial distribution table. All right. What is this? This is a way to do this in an estimated fashion, in some case a lot faster. Now, this can be very easily done on one of the websites that are available, and you just find a binomial distribution calculator and it will do the whole thing for you. But if you don't have a calculator and you want to see how it's done by hand, this is the formula to do it by hand. But after a while, certain probabilities show up more often than others. 17 is rare, but 15% will show up more often, and 15% is right here. There's our P of 15%. Right? So if we scroll to N5, which is right here, this is this whole thing, and we look at X3, N5, X3, and 15%, we're going to get this number right here. It's different than our answer, but if you have questions which have a standardized probability of success in a single trial, you can use a table. I'm sorry. You can use a table to find those probabilities. Now again, for 17 calculations, there are ways around it to avoid doing this all by hand. Again, binomial distribution probability calculator. Google that, see what you can find, or do it by hand. Either one works. So you have this option, you have the table, and you can figure out, which row and which column. I'm very bad at this. Which row and which column falls to it. Again, on top you have the probability. On the side you have the n and an x, and this gives you all those calculations. Again, we're looking for 17%. What you have there is 15. So there is the downside of using a table, because the table has to be compact. It won't have all the little nit and gritties. But you have plenty of choices to do it. Formula, you can find a calculator, you can do it by hand, you can try to use your method. But what we are building right here is exactly what you have there. Again, mind you that our P is 17%, where the table gives you 15. So, careful, don't copy and paste, understand. All right, so that was that. Let's see if we can find the example we've been talking about. Alright, we were on example 7, so let's scroll down back to 7. Alright. And if you complete this. Now, quick note that might save your life is if you're doing this calculation on your calculator, be very careful to include all the decimal places. If you start forgetting decimal places around, you run into a problem of skewing your results. So just take your time and run this, because if you actually do this 0.17 to the third power, that thing gets very big and freaking ugly very quickly. Include extra decimal places. So don't go 0.0049, add that 13. It doesn't cost you anything. Well, it costs you a couple seconds to write it down. Just be careful. Again, if your numbers are different than my numbers in a very small fashion, I'm assuming it's a rounding error and I'm going to let you slide with it. But if your numbers are drastically different, yeah, don't. All right, so this is how you do this. Just plug and play, but understand that there's a lot of really cool things lying around it, just in case. All right. And that was part. Oh wait, there's more. Investigator examines 5 cases of financial fraud every day. Find the most frequent number of cases each day in which the victim knew the perpetrator. Well, alright, so for that we need to pull up, apologize to that piece of paper, we need to fill this out. So if we finished computation of all of those, we would have gotten a set of numbers like this. And the question, or part B, is asking, an investigator examines 5 cases of financial fraud every day. Find the most frequent number of cases each day in which the investigator knew the perpetrator. So what we are asking for is the mode of this distribution. And the mode is the most frequent number. Well, 40% of the times we get 1. 39 we get 0, 16 we get this, 3 we get that, 0.5% time we get 4, and then almost never we get 5 out of 5 cases. Right, so this is this. So if it's asking about the most frequent, we're looking for mode. And then C is an investigator examines 5 cases of financial fraud every day. Find the average number of cases per day. Well, the average number of cases is the sum of x, p of x. So what we need to do is we need to build a column. That's 0, that's 0.403, that's 0.32, 0. Just laziness. And we just sum those up. Right, so that's relatively straightforward, and if we sum it up, that should come out to be 0.8497. Alright, I'm losing my voice. We've been talking for 2 hours, so if you're still awake, go get yourself a copy, pause. I will be here when this is done. So, example 8. Find the mean and standard deviation of the random variable x. Example 7 from this. Alright, well. Example 8. Example 8 is asking us for mean and standard deviation. Well, we know that the mean of a binomial probability distribution is n times p, right? Think about a coin again. If I tell you to flip it 10 times, how many heads are you expecting to get? 5, right? Because it's 50% of the time. 10 times 50% of the time, 5, right? So this is the mean, and the standard deviation is square root of npq. Right, so we know what our n is, and that was 5. We know what our p was, and that was 17%. We know what our q was, that was this, and this marker is dead. So what's our mean? Well, our mean is 5 times 0.17. So our mean is 0.85. Look at that. That's pretty cool. I mean, I think it's really freaking cool that the mean that we calculated here using all this really difficult formula, and the mean we calculated in example 8 using this very simple formula, look at that. How freaking cool is that? Right? And again, which one is more precise? Well, this one is more precise. Why? Because this one talks about this whole population, where we are here talking about rounding for probabilities. Why we are round? Well, because this freaking formula is so crooked. But this is really cool. Alright, let's try the standard deviation. The standard deviation is sigma, and that's square root of 5 times 0.17 times 0.83. So 5, no, square root of 5 times 0.17 times 0.83. Boom. And we get that sigma equals to 0.8399. And again, squiggly lines because we're saying about there. Right? Easy. And again, just appreciate how awesome this is. Like, as far as awesomeness goes, this is pretty freaking awesome. Alright, that being said, let's keep going. Example 9. Do we have space here? Maybe not. Student takes a 10-question true or false exam. Find the probability that the student gets exactly 6 of the questions right simply by guessing the answers on every question. So we have 10 questions and we're looking for probability of 6, right? So our x is equal to 6 because we want to guess exactly 6 of them. And it's true and false, which sounds like a setup for binomial. And, well, you're guessing, aka you're flipping a coin, which means that our p equals to 0.5, which means our q equals to 0.5. So, p of 6 equals to 10 C6. By the way, in some textbook there's another notation you will see something like this rather than this or that. So just mind you that there's 3 ways to write this. I choose to write this because for me that makes more sense, but again, because I kind of skipped this explanation in the book, I just kind of give it to you rough shove here. That's the formula. Alright, this 1/2 to the 6th power, and then 1/2, well, this is the 50%, to the 4th power. Alright, so 10 C6 times 0.526 times 0.524, bam, and we get what? Probability of getting 6 of them right on an exam is 20.51%. Alright, well, let's pull up the table. And let's see. 0.5 is this column right here. This column right here. Right, next page. Here it is. 10, 6, 6 at 0.5. Let me do this. Right? And again, in this column, the first column, we look at for our n, which is the number of trials. In our case, that was 10. In the second column, we're looking for the number of successes. Again, in our case, we wanted 6. And then in the top column, which is this one, we're looking for the probability of a success in a single trial. And again, in our case, that was 50%. And then we go down to whatever we were looking. We're looking for 6. And this is the number we're getting. 20.5%. Again, our answer is a lot more precise, and then if you look at our calculator, that answer is exactly 20%, 0.5078125, and so on and so forth, which means that the actual answer is a lot more precise if we do it this way. We get a lot more precise answer than if we do the table, but the table is a lot faster. And again, 50% is a common thing where 17 wasn't. So there is that. Now let's look at what they say next. Part B, find the probability that a student will obtain a passing rate of 60% or greater simply by guessing. Probability that they will obtain a 60% or greater by simply guessing. All right. 60% or greater. So grade of 60% or up means he needs to score an X greater or equal to 6. Which means that he needs a P of 6 or a P of 7, or to get 8 of them right, or to get 9 of them right, or to get 10 of them right. Okay, if we use the table I have provided you guys, what you will see is that P of 6 is right there, so that's P of 7 is right underneath it. P of 8. Sorry, there's another 0. P of 9. And P of 10. And that's the answer. You sum those things up and you get the answer. Let's see. Now here's the part which I know will cause a certain level of confusion, and the part is that if you look at, now I'm looking in the example 9 solutions, what they're saying is using the table, use P smaller equal to 6 minus P smaller equal to 5. We're talking page 71. Now, the reason for it is that the table that was initially included in the book was a cumulative probability table for binomial distribution. An accumulative probability table, what it does, it has the same setup as our table, which has a P, an N, and an X. So if you had 10 here and then 0, 1, 2, 3, 4, and so on and so forth. What it does is when it gives you a probability for right here, for this number, what it really does, it gives you the sum of all those probability. So it gives you the sum from everything from 0 to X. Right, so The table that was included in the book was that I found the table to be highly unreadable, so I gave you the table packet, and I haven't gotten around to changing the problems. Again, if you understand how the problems look and behave, then solving them is relatively straightforward. And again, because the tables that you're going to be using might be different than the tables I'm using or I'm recommending, I suppose that's the price of having a free textbook. It requires you a little bit more work. Now again, if you ever end up with a table that just doesn't make sense, or you found a table you like and it doesn't match what we have and how I solve problems, link me the table or send me a picture of it and I'll figure out how to use it and I will let you know. So again, if you're looking at examples, as long as you understand what we're writing here and how we are approaching the problems, you are going to be fine. If you're just copying and pasting and putting formulas in, you're in for a surprise, because again, there's limitations on how much information I can put in a book in a short amount of time. Alright, so that was 9. Let's keep going. Let's kill this and let's see. Number 10. An appliance repairman services 5 washing machines on site each day. 1/3 of the service calls require installation of a particular part. So, example 10, n equals to 10, p equals to 1/3. The repairman has only one such part on his truck today. Find the probability that the one part will be enough today, that is that at most one washing machine will be serviced will require this particular part. So what we're looking for is this. Right? Again, at most 1. At most 1 means 0 or 1. So this means probability of 0 plus probability of 1. Alright, well, solve it. P of 0, that's probability of 0 equals to 5c0 1/3 to 0 2/3 to the 5th power. What? Sorry about that, because our Q is 2/3. So that equals to 5 times 1 divided by 3 to 0 times 2 divided by 3 to 5th. And that comes out to be 0.13169. And the probability of 1 equals to 5c1 1/3 0 2/3. No, 1/3 to 1 2/3 to 4. 1 success. And 5 probability. So 5 probability. So 5c1 times 1/3 to power of 1 times 2/3 to the power of 4. So probability of x smaller equal to 1 equals to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that's 1, 9, 0, 6, 4, 0. So that's 46.091%. All right. Now I'm looking at the solution. It says use cumulative distribution table, chapter 12 appendix. We don't have a chapter 12 because I didn't retype the whole textbook. I retyped only the parts which were relevant. So if it tells you to use a cumulative distribution table in chapter 12 and you have no clue which table to use, or you're looking for it and it's not there, just post it on Piazza. I'm going to do it. I'm going to just post the chapter 12 appendix table that I found, and we will take it from there. But just heads up, if there's things that I haven't removed or rephrased, don't panic. I got you. Well, I might be got you. Maybe got you. Gets got. Whatever. Alright, part B. I'm getting tired here. Part B. Find the minimum number of such parts he should take with him each day in order that the probability that he have enough for the day service is at least 95%. So we want the probability of x smaller equal to let's call this number r, such that it's greater or equal to 95. And we're looking for the question of r. How many parts we need to do? Well, if we take 2 parts, that's 46. If we take 3 parts, what do we have? Well, 3 parts, that's 5c3 1/3 to the 3rd power. Oh, hang on, 1 times 2/3 to the 4th. And then if we take 2 parts, that's 5c3 1/3 to 2nd power, 2/3 for the 4th power. And then if we take 4 and so on and so forth. So let's calculate. 2 would be 5c2 times 1/3 squared times 2/3 to the 4th. So this would be 0.2194. That's 60. Yeah, that's still too small. So that's still small. Let's try the 3rd one. 5 probability 3 times 1 divided by 3. No, I'm making a mistake somewhere. Hang on. 2, this should be a 3, and this should be a 3, and this should be a 2. Okay, I have to redo that one. And this should be a 2. Sorry, this should be 0.3292. 70. So 0 is 13 plus 32, 46. We got 46%. If we add 2, that's 78. 80, 896. So we need to go to 3. But this seems like a lot of work. Hang on, let's see if we can find an easier way to do it. Let's see if we can pull this up. All right, cool. So let's pull up. Let's pull up. Let's go. Alright, so here it is. Binomial probability calculator. Let's try one of them, see how it goes. Probability of a success in a single trial was 30%. 3. Number of trials was 5. Number of successes, we said 3. Calculate. And what we have here, zoom in a little bit, and what we have here is all the little things. So the probability of getting 3 successes, we got 16%, right? And there's our 16% right here. And then probability of being less than 3 is this. Probability of being equal less than 3 is right here. Let's see if we can let's see if we can find another one that works better. Binomial cumulative. Number of successes, number of trials, 5, 3, calculate. Cool. Another one that works. Let's see if we can find another one. Let's see, how is this one? No, that's the same thing. No. Anyways, you have options to do it with a calculator. So for example, so what I did here is I just went Googled binomial probability calculator. I went to the StatTrak one. I filled in the blanks we had, and it does the calculations for you. You just have to understand what all this means. Here it means the probability for the number of successes you put in the first one. The second one means smaller, smaller equal, greater and greater equal. And you have this kind of approach to solving this. So StatTrak is one of them that works pretty nice. Social science, calculator works pretty well. It's another one of those that has some descriptions. Let's see if it has binomial. It has histograms, has pooled data, calculators, binomial. No, I don't see it has binomial. So binomial, we have to go somewhere else. But this information is available. So if you don't want to crunch numbers and you know how to do it, you just don't want to do it, there are ways around it, and that's one of the examples. All right, let's go back and let's pull up the examples. All right, so what do we have? Oh yeah, we solved this. All right, so that's about it. I will find the chapter 12 appendix table. I will see where I took the book from and see if they have the chapter 12 available to it, and I'll post it up. And that closes up chapter 4, I think. Yep, that closes up chapter 4. So I will post this, or I will do my second attempt at reposting this today, and then I will do the updates and the links. If you have a question about it, you found a calculator online that works and you don't know if it's the right one, just ask. If you have some tables that you got from some textbook, great. If you have some textbook that you borrowed from somewhere, great. If you found one online, great. Use it. I value your brain more than your ability to crunch numbers. I mean, if you're a freshman in college, yeah, crunch numbers. But if you've been around the block once, don't. Your brain is too valuable to be used for number crunching. All right, in that case, I'll talk to you guys later. Thank you.